Hey everyone, hope you all had a good Thanksgiving break. You all ready to get going here? We have 2 class periods left and then we have a final exam. Today I'm not talking about the final at all. I'm just going to continue to move the train forward here. Try and get as much as I can done. We are talking about series, and specifically last time we talked about power series. So I just emailed this file to you. This is just an overview. It's not something that you need for the test or anything like that. It's just kind of get us to be thinking about the big difference between a series and a power series. So 8.2 through 8.4 was all about series. And we said a series is just the sum of a sequence, just basically adding up a bunch of numbers. And the notation that we used was over here. We said sum n equals 1 to infinity. And then when we define power series, we started the index at 0. So we can also start the index at 0 for a series. So it's a dummy index. It doesn't matter where it starts. But when we first introduced the idea of a sequence, we always started at 1. But now we can kind of extend the idea to start it at 0. So we know that when it comes to a series, which is just the sum of a bunch of numbers, that's either going to converge or diverge. And when it comes to converging, there's only 2 types of series that we can find the sum of. And that's a geometric or a telescopic, if they converge. Otherwise, it's basically just a thumbs up or thumbs down in terms of convergence or divergence. And to figure that out, we have to run tests. And we have that big formula sheet with all the different tests on it. That's series, adding up a bunch of numbers. A power series, on the other hand, is a series that contains numbers. Okay, the C sub n here is basically a sequence of numbers sitting in front of a bunch of powers of x. And here's the general form of it. We call this a power series about a, or centered at a. We talked about this last class. And if we let a be 0, then it's going to look like this. I'm missing an equal sign right here. I just realized that's supposed to be equals right there. Equals c sub 0 plus c sub 1 times x, blah, 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 the rest of the way. So that's a power series about 0. So when it comes to a power series, the convergence or divergence of that power series depends on x, because x is like a variable now. If we assign a value to x, then it might converge and it might diverge. So with that idea, what we did is we said we can define a function to be a power series, and then that function would be well defined so long as the x that we plug in gives us convergence. And so the domain of this function is all the values of x for which it converges. And we started talking about that last class. And I also showed you this, that when it comes to any power series, there are only 3 possible outcomes when we're talking about convergence. It's either going to converge at a single point, x equals a, or it's going to converge on any value, for any value of x, which means it converges on the entire number line, or it's going to converge on an interval. Those are the only 3 possibilities. And if it's an interval, then when we set up the ratio test, we're going to get an inequality that looks something like this. And the capital R here is referred to as the radius of convergence. And then when you go and actually try and find the interval itself, there's 4 possible outcomes when it comes to the types of intervals you can have. And whenever you get that answer, that's called the interval of convergence. Now, I just stated we're always going to use the ratio test when we try and figure out the convergence of a power series. Now, last class, we did 2 examples. I know that was a long time ago, but we did our first example was this one. We said, for what values of x does this converge? So we ran the ratio test, and we determined that when we get to this point of the ratio test, this expression went to 0. And so it doesn't matter what x is. Regardless of x, this thing is always going to stay less than 1, which satisfies the ratio test, which means that we can plug in any x, which means that it converges on the entire number line. So it converges for every value of x. So we had that example, which would take care of.
I have a question right here.
Uh-huh.
So for even whatever ratio test we're using, we always separate the x away from the a sub n and b sub n, always?
Yeah, you always separate that out and see what happens with the stuff that has n in it, because the limit is with, it has n going to infinity. X has nothing to do with the limit.
Okay, perfect.
So the example I gave you that I just showed you that we did last class was an example of case 2 here, where it converges for any value of x on the entire number line. And then I gave you another example at the end, the very last one we did, where we did this one, we did the ratio test, we ran through it, and we determined that this, when we took the limit, this went to, well, this went to 1, and we still had a 5 there. So we had this absolute value of 5x is less than 1 is what it's supposed to say here. This is what we had. We had absolute value of 5x is less than 1. So if I divide both sides, well, I can rewrite this as 5 times the absolute value of x less than 1. And if I divide by 5, I get this. If you look at it like this, then this looks like x minus a less than r. And so what I'm trying to get you to see here is that our radius of convergence would be 1/5. And we did this, we worked through this, and we solved the inequality, and then we had to check the endpoints. We checked the 2 endpoints, and we determined convergence at one endpoint and divergence on the other endpoint. And so we got an interval of convergence right here. That was our interval of convergence. So there's a big difference between radius of convergence and interval of convergence. The radius of convergence is just a number. In this case, it would be 1/5. And the interval of convergence is actually the interval, which you have to do a lot more work to get. Those are the only 2 examples I gave you, right? So, oh, in what case was this? This case would have been case 3, where we actually have an interval. What I have not shown you is an example where it converges at only 1 point. So I'd like to give you an example of that, and that's what we're going to start today. Any questions?
Is this the file we received on the email?
It should be. It should be. I just emailed it like right before class.
Okay.
So here's the series. I want to know for what values of x does this converge? Okay, this is going to be the answer, but just ignore that for now. Okay. So what we need to do is run the ratio test. So when we run the ratio test, we're going to do the limit as n goes to infinity. Okay, first thing we do is we plug n plus 1 into this. And we divide that by just that without just leaving n as n, like that. And since it's not a fraction, I don't have to do like reciprocal. It's just something over its, you know, there's no fraction. So I'm just setting up the ratio as you can see here. All right, this limit, I'm going to clean up the factorial. I'm going to rewrite that as n plus 1 times n factorial. Then I'm going to rewrite x to the n plus 1 as x to the n times x. And then over n factorial x to the n. Oh, we need this to be less than 1, right? For the ratio test to work. So, or to get convergence. So we get stuff to cancel here. And now we have this very interesting limit. The only thing that's left here is the n plus 1 and then times x. And we need that to be less than 1. But there's a problem. Do you all see that no matter what I pick for x, right? This thing right here is headed to infinity, right? So if you fix a value of x and then that n plus 1 blows up, it's never going to be less than 1 unless you pick x to be what?
0.
0. And that's the only number that would make this thing stay less than 1. The important thing is that you're going to fix x. You're not saying let x get close to 0. So it's not like a limit. You're setting x to be 0. So if x is 0, then of course this thing here is true, right? Which means we'd have convergence. That means that means therefore this series converges at x equals 0, which is a single point.
So can we take the L'Hopital rule for the n+1?
Why would you need L'Hopital's rule?
No,
You
I'm
don't
just
have
asking.
infinity. You don't have infinity over infinity,
True.
right? You just have infinity. It's just getting huge, right? That's it.
Mhm.
So back with what I sent in the file, it says here that if you're given a power series, there's 3 possibilities. The first possibility is that it converges only when x equals a. Now, x equals a, that means that this piece right here, you have to pick an x which makes this 0, right? Like if I let x be a, like if that x is a, then this is a minus a, that's 0. Well, for our problem, this right here is really like x minus 0 to the n, right? And so if I let that x be 0, then of course this will be 0 minus 0, and that should be 0. So you're adding up 0 infinitely many times, you get 0. Do y'all see how that's this first case? Do y'all see that?
Yes.
Okay, and then the other example we did last class was this case, and then the other example we did last class was the third case. So I've given you an example of each of those cases. So here they are kind of summarized. The 3 problems I did last class right here. All right. The first one we did, the interval we said was everything. And therefore we say the radius of convergence is infinite. The second problem we did, this was the interval. And I showed you that the radius of convergence was 1/5. And then the one we just did, there was only one answer, right? There was only one point where it converged, x equals 0. That's not really an interval, it's a single point. And then notice that we say the radius is 0. And that's because, how wide is a single point? A single point doesn't have any width. So we say that the radius is 0. Okay, now I have another example here for us. That's not it. This is a classic problem here. Where is it? There we go. So same question here. I want to know, well, you know what? Find capital R, and I'm going to abbreviate this IC for interval of convergence, all right? For this series, sum n equals 0 to infinity of -1 to the n x to the 2n over 2 to the 2n times n factorial squared. This is actually a famous series. It's known as it's a function, right? I mean, this is a function so long as there's some x values that make it converge. This is known as the Bessel function. And Bessel functions are used to model things that vibrate. Like if you think of like a drum, a drum usually has some sort of membrane that's stretched over the top. And when you hit the drum, it vibrates. You can use Bessel functions to model the shape of the drum at various points in time. Now, I mean, when you hit it, it's hard to see the membrane vibrating, but it is, right? It's not flat. It's moving, and different parts of it are higher than others and lower than others. So anyways, that's what they're used for. One of the things they're used for. All right, so we need to figure out the radius of convergence and the interval of convergence, which means we need to run the ratio test. All right, here we go.
So since ratio test is always absolute, we won't care about the alternating sequence, correct?
That's right. We don't need to worry about the -1 to the n. We can chunk it. If you don't want, just get rid of it, because yeah, you're gonna take the absolute value. Now we do need to replace all the n's with n plus 1s, right? So be careful there because that is going to distribute. The 2 is going to have just to distribute okay, so that's the series, well, the sequence part of the series with n plus 1 in there. And then I'm going to divide by the original sequence, but I'm going to flip it, right? So 2 to the 2n on top, and then n factorial squared, and then on the bottom x to the 2n. Yeah, and we threw away the -1 stuff. Let's just get it out of there. All right, now before I do the next step, just keep in mind that all of this is really x to the 2n. Yeah, I'll do it all. Yeah, all right, that's x2n plus 2. That is 2 to the 2n plus 2, right? That's what those are. So when I rewrite this limit, I get x to the 2n times x squared over 2 to the 2n times 2 squared. So that's just splitting it up using properties of exponents, right? And then this n plus 1 factorial squared, I'm going to write that as n plus 1 times n factorial, but then all of that squared. So I just rewrote n plus 1 factorial as this. And I'm hoping you are all comfortable with that by now because we've done it so many times. We need that to be less than 1. All right, some things cancel, but let me do one more thing. Since there is multiplication right there between the n plus 1 and the n factorial, I'm going to rewrite this as n plus 1 squared times n factorial squared. So I'm squaring each one. I'm squaring that and I'm squaring that. And that's going to allow me to do some nice cancellation now. This gone, this gone, this gone, it's gone, that's gone, that's gone. Okay, let's put everything that is not with x out front here. So I think I have a 1 on top, don't I? Just 1. On the bottom, I've got a 2 squared, that's 4. I have an n plus 1 squared. And I think all I'm left with over here is an x squared. Do you all agree? Okay, now let n go to infinity. If n goes to infinity, this thing goes to 0, which means regardless of what I choose for x, no matter what I choose, right? I'm going to multiply times something that's headed to 0. That should always stay less than 1. Now, keep in mind, don't lose sight of this. X has to be a real number. X can't be infinity, all right? We're not letting x approach infinity because, of course, if x became infinite here, then you'd have infinity times 0, which is an indeterminate form, but that's not the case. We are fixing a value of x. So it's got to be a real number. I don't care if it's a trillion, cajillion, gazillions raised to the whatever. That multiplied times something that's headed to 0 is eventually going to be less than 1, eventually. So this is always true, right? Regardless of x. Always true. So which of these 3 cases do we have? 1, 2, or 3?
2.
We have case 2, right? We have case 2. So we have case 2, which means that the radius of convergence and interval of convergence are, let's see.
How do we know it's case 2?
Because this goes to 0, so this inequality is true regardless of x, right? Any x we plug in will make this less than 1, which
Correct.
means that regardless of x, this thing converges. And case 2 says it converges for any value of x.
So it could be a positive or a negative, yes.
Right. Does not matter. Does not matter. So the interval of convergence is any value between negative infinity and infinity, and the radius of convergence we will say is infinite. In other words, this is a well-defined function. If we call this thing f of x, well, actually, because it's a Bessel function, they actually, this is the notation they use for a Bessel function. Capital J, subscript 0. This is a Bessel function of order 1, or sorry, of order 0. It's called an order 0 Bessel function. There's an order 1, an order 2, an order 3. They're different order Bessel functions. If we define it to be this, that is the Bessel function. And it is defined everywhere, which means if we graph it, we should see a graph everywhere. All right, I'm going to show you the graph of the Bessel function now. That's it right there. So what you're seeing right now is just the first 2 terms in the power series graphed. So remember, when you have a power series, you first let n be 0, right? And you plug it in, you're going to get something times x to a power. And then you let n be 1, and then you're going to have another number times x to a power. And then you let n be 2, and then you're going to have another number times x to a power. What you're seeing in this graph is just the first, I think I have there, that's the first 2 terms. But as I go further and further and add more of the terms, you'll start to see the Bessel function come to life here. You ready? Here it comes. So it keeps going out forever, but can you all see that this almost looks like a sine function that's kind of what we would refer to as being dampened? So as you move out to the edges, you're losing amplitude on it. And that's kind of the way these things would behave. Imagine that the edges of your drum, you know, where the membrane goes around the edge of the drum, that's going to be fixed to the edge, right? So you might have a vibration in the middle that's big, but as you go to the outside, the vibration has to dwindle away to nothing. Does that make sense? Yeah? Yeah. Okay, so there it is. That's a Bessel function. So we're done with this section. 8, no, we're not. Sorry. Yes, we are done with this section. The only thing in 8.5, and it's a major thing, problems 3 through 21 or 22, those problems in 8.5 are all asking you to find the radius of convergence and interval of convergence for some power series, which means you're going to run the ratio test and you're going to see which of these cases you have. All right. So make sure you work through the homework on those, because I know for a fact that there are problems in the homework that I just have not been able to show you examples similar to those. So you need to see the sorts of algebra and the limits that come into play and how you determine the capital R. There's just not enough time for me to go through 5 more examples of this. Okay. All right, we are moving on to 8.6. So 8.6 is called representing functions. I got a new keyboard and my fingers and my brain are still trying to do my other keyboard, which was much smaller. As power series. I'm making excuses for being a horrible typist. Is that right? Okay, representing functions as power series. So what we did in 8.5 is I would give you a power series, right? And I would say, hey, tell me where this power series is defined. Where is it a function? Like if I give you a power series, give me the domain of the function. That's basically what we're doing in 8.5, what we were just doing in the previous examples. Now we're going to do something different, which is more applicable to the real world. If I start with a function, right? Give me a function, some function that you've been using your whole life. Is there a way to convert that function into a power series, right? That's more useful to us. Now in 8.6, we are going to focus all of our attention on one function and how that one function converts to a power series. And then in 8.7, we will have a general formula to convert any function into its power series. So just keep that in mind that right now we're very limited. We're just looking through this very narrow field of view at one particular function, and then we'll generalize in the next section. So recall this series that you should all be intimately familiar with at this point. That's not a power series, is it? That's just a series.
Correct.
Okay, now what type of series is that?
Geometric.
Geometric, okay? That's a geometric series. When does it converge?
When the n is less than 1.
When the absolute value of r is less than 1,
Oh, yes. Yeah,
right? Okay, so that's a geometric series. Now, let's write that series out. I just want to write it out. If n is 0, we get a, and then we get ar, then ar squared plus ar cubed plus ... right, forever. Now, assuming that the absolute value of r is less than 1, okay, so I'm telling you, assuming that this converges, all right, what does it converge to? We know, right? We have a formula. What does that converge to?
A over 1 minus r.
1 minus r. Okay. So now that's so long as if the absolute value of r is less than 1, then we know that that's true, right? Yep. Okay. So now here's what I'd like for you to do. I'd like for you to let a be 1, and I'd like for you to let r be x. And I want to tell you that the absolute value of x is less than 1. Let's see what this thing turns into. So sum n equals 0 to infinity. All right, a is 1, right? So I don't even need to write a anymore. A is just 1. And then x, r is now x. So this is just going to become x to the n. This should be equal to, let's just write this sum out. A is 1, r is x. 1 plus x squared plus x cubed plus ... What can you tell me that is equal to?
1 over 1 minus.
Yep, 1 over 1 minus
R, which is a 0.
r is x, right?
Oh,
So
yeah.
1 over 1 minus x, right? 1 over 1 minus x. Now, keep in mind, that's only if the absolute value of x is less than 1, right? If the absolute value of x is less than 1, then that's true. So what we just kind of concluded here is this. If we define a function f of x to be the function 1 over 1 minus x. Now that's a function that you may have studied in college algebra, right? This is a rational function, right? This function is actually equal to 1 plus x squared plus x cubed plus x to the 4th plus ... forever if the absolute value of x is less than 1. So like, for example, if you wanted to, if you plugged 0.5 in here, 1 over 1 minus 0.5, you would get the same answer that you get if you plugged 0.5 into here. All right, that's what we're saying. Now, I want to show you this graphically to see if this helps make sense as to what the hell I'm talking about here. All right, here we go. There's the graph of 1 over 1 minus x. Okay, college algebra, rational function, we have a vertical asymptote. Now, here's the power series that we just came up with. Sum n equals 0 to infinity. It's going to go to infinity. Let me draw this back. Of x to the n, right? So this is going to be 1 plus x squared plus x cubed. So I'm going to show that to you already. Here it is. Now, here's only the first term, but I'm going to start adding more terms, and I want you to see what happens. See what's going on here? Do you see that thing, this red graph is kind of trying to like map itself onto the black graph? But only in this one little region, only between -1 and 1, right? Because that's our interval of convergence. That's the only place that that power series is valid. If you go outside of that interval, then this is no longer, the power series no longer matches the function. Let me back it up. So here we have a bad approximation. The more terms you get, just watch what happens. Look at this gap right here. Okay, just look at that gap. Watch how it starts to close the further out I go. And if I could go to infinity, it would close the gap completely. And this little piece right here, if I kept going, is going to get closer and closer. And this little thing will start marching its way over. And then if you could go to infinity, it would give you, they would be the same function. Okay, it would be the exact same function. Is that clear?
When you're adding those terms right there,
Yep.
that's just is that just the like the 1 plus x squared? So the farther you go, so if you go 15, it's like x to the 50th, and it just
Exactly. So look, right now what we're looking at, if you look at the graph right now, this is just, let me do it this way. So remember, the sum n equals 0 to infinity is x to the n is equal to 1 plus x squared plus x cubed plus ... And we're saying that this is equal to 1 over 1 minus x, so long as the absolute value of x is less than 1. So right now, what we're looking at here is just if we were to graph, if we were to be graphing just this first one. Okay, that's the function. Oh, sorry, it's the first two actually. It's 1 plus x. Do you all agree that that's 1 plus x? And now if I go one more term, now I'm going to have a parabola. So that's going to be 1 plus x squared. So there's a parabola, and it's not bad. It still sucks, but it's not bad. Now here's it. Next one, I'll have a cubic function. There's a cubic function. See it? It's better. Now next one, I'll have a 4th degree polynomial. Oh, there it is. It's better. And so when I go out here, now I've got all the way out to like x to the 23. And you can see it's really good, right? But remember, it's going to infinity. That's the whole idea, is that if we go to infinity, they're the same function. They're the same function. And I know you're going to sit there and go, but you can't go to infinity, right? So why is this useful? And it comes down to the idea that if you can do this for any function, take it and create a power series from it, then everything else in calculus becomes easier, like integration, differentiation. Like, what would you rather integrate? Would you rather integrate this or integrate this? Like if I asked you to integrate one antiderivative, you just say x, right? Antiderivative of that, 1/2 x squared. Antiderivative of that, 1/3 x cubed. Antiderivative of that, 1/4 x to the 4th. Easy does it, right? Doesn't get any easier than power functions when it comes to integration, right? This, well, that's easy too, because it's just a natural log. But still, think about more complicated functions. If we take a function that's very complicated, if there's a way to write it with its power series, then you can integrate it. And of course, you'll have to stop somewhere because it goes forever, right? You'll have to stop somewhere. But in the real world, right? If you're manufacturing something, your machines are only so precise anyway, right? So approximations are okay in the real world, right? It's okay. If you need to be more precise, I mean, maybe you just need the first 3. Maybe the first 3 is good enough, but maybe you need the first 50. There's always going to be a little bit of error in that, but we can measure the error, and then we can say, oh yeah, just go out to the 20th term and you're good, right? Does that make sense?
Yes.
Okay. All right. So we are going to now get this out of here. Whoa. What was that? I have no idea what I just did.
I think there's a cross right at the bottom.
No idea. That's real weird. I think I'll just reopen it. All right, back to this. All right, so here's what we know, right? This is it. This right now is our master. I told you this section, right? This section, we are going to look at one function and one function only, and look at its power series. And that's all we're going to be focusing on in this section. You ready? This is it. This is the one right here. Now we're going to build off of this idea. So now what I'd like to do is I'd like for us to, I'm going to leave that there. I'd like for us to find a power series, I'm just going to say PS, for f of x equals x cubed over, now I want to do the same problem that I have ready to go in the graph, x plus 2, 2 plus x, x plus 2. All right. Now this and this don't look like they have anything related to one another, right? This has a 1 up top, this has an x cubed up top, this has 1 minus x, this has x plus 2. They don't look like these could possibly be related at all. But I'm gonna do some algebra, all right? We're gonna have some fun with algebra now. Do you agree that this function is the same as x cubed times 1 over 2 plus x? So I just pulled the x cubed out front. That's just algebra, right?
Yes.
Okay. Now, I'd really like to have here underneath 1 minus x, but I don't. I have a plus and I have a 2 here. So I'm going to factor the 2 out. We've played a game like this before, kind of, with integrals. We've had to do some weird algebra like this. I'm going to pull a 2 out of the bottom, and it'll leave me with a 1 plus a half x. So I factored a 2 out of both of these. That equals, that 2 that's on the bottom, I'm bringing it out as a 1/2 in front of everything. Now watch this. 1 minus negative 1/2 x. So I pulled the 2 out, right? That when I pull a 2 out, I have to put a half here. That 2 comes out as a half out here. And then I rewrote the plus as a minus minus. Yeah?
Yeah.
Now, go back up to this formula we have. Do you see that I have 1 over 1 minus x, right? And that equals 1 plus x squared plus x cubed plus x to the 4th. The x here is kind of a dummy variable. You can look at that as being, if you ever see 1 over 1 minus a green box, that should turn into 1 plus the green box squared plus the green box cubed, right? So long as the green box absolute value is less than 1. So at this point, I'm going to say that this is equal to 1/2 times x cubed times the series n equals 0 to infinity of what?
1 over 1 minus x.
No. I'm turning this whole thing into a series. What is the series it's turning into? Right here, this 1 plus x turns into this, right? Maybe I should include that right here. This equals sum n equals 0 to infinity of x to the n, right? The x is this. So what would go here?
Negative 1 over 2x.
Negative 1 over 2x, negative 1/2 x to the n. Now, that's only legal, okay? This move from here to this is only a legal move if what? The absolute value of what is less than 1?
X.
The x, the dummy variable.
Not x, but what was x for us?
R.
Which was
Negative 1 over 2x.
negative 1 over 2x. See, this green thing is like, the whole green thing is like the x. Do y'all see that? That whole green thing is like the x's. If you don't like that formula up there, just go up to this formula, replace all the x's with u's.
Okay, so -1/2x. Are we looking the whole, since we're looking the whole thing as x, so like, I don't understand how is it like less than 1 if we just multiply it with a bigger number, for example, like 5, it's not gonna be less than 1 then.
Okay, so if I plug 5 in here for x, this is not going to be true. I
Yes.
agree. That's not what we're saying though. We're saying that this switch to change that part over to this power series, in order to change this to this, I am restricting you to only being allowed to plug in x's that satisfy this equation. It's like this picture I showed you a moment ago. These two only match up in that little window. If you go outside that window, this is no longer valid.
Oh, okay. So I understand the term when you use restricted.
It's a restriction. That's right. It's a restriction that this is true only if that's true. Now, let's just clean this up over here. This is really 1/2 x less than 1. Let's bring the 1/2 out. And let's multiply both sides by 2. So our radius of convergence is 2. Because the absolute value of x has to be less than 2. This was just algebra, right? I dropped the absolute value off the 1/2. And then, well, I took the absolute value of negative, and it's be positive, and then brought the 1/2 out, multiply both sides by 2.
So, Professor, what is the radius of convergence for in cases like this?
I'll show you. I'll show you with a picture. Let me finish though, because we're not done. This is where we are right now, right? And the instructions said to find the power series for this. Here's what we have so far, everything in black. So watch what I do now. Sum, let's put the 1/2 x cubed in front. Watch what I do on the inside. This is a very important step. -1/2 to the n, x to the n. So because -1/2 and x are being multiplied, I apply the n power to both of them. So I get this. And then check this move out. I'm going to bring the x cubed inside because this sum has to do with n. This has nothing to do with x. So this is almost like a constant that can come in here and be multiplied through. So I'm going to have a 1/2. I'm going to have a -1/2 to the n, and x to what power?
Cube. 3. X to 3n.
N plus 3.
N plus 3. N plus 3. Because we're doing x to the n times x cubed. And so when you put those together, you get n plus 3. So look, my goal right now is to do this. My goal is to get you to a point where you have this. That's what a power series looks like, okay? We have to have some numbers in front, things that are changing, but they're numbers. Then you have to have x minus some constant to the power n. That's what we need, okay? Do you all see that all of this out front can be our c sub n? That as n changes, that this is going to change and you'll just get a different number out here every time. You'll see that? And then here, this is x to the, and well, this is n plus 3. And that's n, right?
So we can just separate it.
Well, so we need to do something about this, all right? Now, here's what we can do. I mean, technically this is right. I mean, this is a power series, but if we wanted to make it have a power of n, we're going to do something. Let me just time out for a second. If you get to this on the test, I'm happy. Okay, I'm happy. But there are more complicated problems, which we are not going to do in this class because we just don't have time, okay? There are complicated problems where you actually have to put two power series together, and to put them together, you actually have to make that power be an n. So I'm going to show you how to do it. That way you know how, like you've seen it, okay? I don't want to leave it out. So if I want that to be an n instead of an n plus 3, here's what I'm going to do. I'm just going to imagine I don't want that 3 there. So what I'm going to do is I will need to subtract a 3, right, to get that to get out of there. So here's the idea. I'm going to go everywhere I see an n, okay, everywhere I see an n, I want to replace it with n minus 3. So just think about what would happen. If I replace that n right there with n minus 3, it would be n minus 3 plus 3, which would just be n, wouldn't it? Yes, but I've got to do it everywhere. Okay, I've got to do it everywhere. So my new sum becomes this. Sum, not n equals 0 to infinity, n minus 3 equals 0 to infinity. I know that looks really weird. 1/2 times negative 1/2 to the n minus 3 x to the n minus 3 plus 3. Okay. Let's see what that does. Sum. Can somebody tell me what I'm going to do for this bottom piece?
Are you gonna make it n equals 3?
N equals 3. Yep. I'm just going to add 3 to both sides of that equation. So our series is actually going to start at 3, not at 0. Go to infinity. And then I'm going to have 1/2 times negative 1/2 to the n minus 3. And then x to what power?
And
There we go. And now we have a power series that looks like this, with the exception of where we start, right? We don't start at 0, but that's okay. Your power series can start wherever. Just to make it look like this form, we have a c sub n. Here's our c sub n. That matches this. And then this right here matches up with this thing. So what's a here? What's a?
0.
0. Okay, so this is a power series centered at 0. All right, y'all ready to see this? Good, you're going to see it now. Here it is. So here's the original function. This is x cubed over x plus 2. Good old function from, college algebra or wherever. Here it is. We have found a function that is equivalent to this function so long as you're in a little window, -2 to 2, radius of 2. So here it is. You ready? Here's the power series. There's the first piece of it. Now I'm going to start adding more pieces in and watch what happens. Now I'm only allowed to look between here and here, right? So in between here and here, they should match up pretty good. Depends on how far out I go, right? But they're pretty good. I think I've brought the computer to its knees here a little bit. Yeah, it's having trouble with that. It's a lot of work to have the computer do. All right, there it is. If we can make that series go out to infinity, they would be the same exact functions on that interval. So you might be asking yourself, well, this kind of sucks that we have to only look in this little narrow window, right? I mean, what if we wanted, what if we were interested in what was happening to the function like over here? Like maybe we want to know what's happening over here. We want to approximate the function over here. Well, remember how we said we were centered at 0?
yes,
All we'd have to do is shift it left or right. And do you remember in college algebra, pre-cal, how do you shift functions left or right?
by -3, I mean negative or positive integer by adding or subtracting.
You put it in the function though, don't you?
Yes.
Like you do, if you did like -3 in the function, it would move it to the right 3, and if you put +3 into the function, it moves it to the left 3. So that -a that we're seeing in the power series, that -a allows you to shift left and right. So you can always go wherever you need to go. If
So
you need,
question. So if you go back to the graph and let it go to infinity, like without the intervals, so what's going to happen then?
I can't because the computer's not going to let me go to infinity. But I'll tell you what would happen. If you could go to infinity, all right, if you could go to infinity, then the red graph will be exactly on top of the black graph. They will be the same exact functions. There will be no gaps between them at all.
Okay, I understand.
Okay.
So essentially, we need this we need this formula or our result, but if we want to see how far, or if we want to get closer, instead of getting a new formula with new numbers, we just shift them and we'll get the exact same path. Is that correct?
Yeah, I think
Instead of having, call it integrals, having different integrals from different sections, we just need this formula and just shift it to replicate exactly the path that we need to follow.
we would have a new formula though. We would have a new formula because the x minus, you would have an x minus a wouldn't be 0 anymore. So it would be a different formula. You can't just go in here and just replace that with like -2 to shift it to the right 2. You'd have to start over from the very beginning.
Okay.
Now it's not going to be that, it's not going to matter that much to us, okay? Because really the functions that we're most interested in, the interval of convergence is everything, which means that it works all the time and you don't have a window that you're restricted in. This particular function has restrictions, so we have to worry about it. Okay, let's do another one. Let me see which one I want to do next. Yeah. Okay.
So for the homework, would you recommend to do all the examples or just half of the chapter?
For 8.6.
Yeah, since we're not gonna have, we're not gonna go in depth.
I'm going to probably tell you to stay. Numbers 3 through 9, 3 through 10. Probably if you can do those, you'll probably be okay.
Okay.
I was going to state that later, but I'll just say it now. Okay, find a power series for this.
We're still looking at the function 1 over 1 minus x, correct?
Yep. As long as we're in this section, that's all we're going to talk about. I have 2 more examples. All right, now you might be tempted to do this. And I agree that this is true. And I would agree that you could write this as a power series and write that as a power series. Because each of these, that's exactly what I just talked about, right? That's a power series, that's a power series. As long as the absolute value of x is less than 1, then I can do this. Here's the problem. This answer is not a single power series. It's the product of 2 power series. So the question becomes, how do you multiply 2 power series together? It's not easy, okay? You can't just, it's not this. It's not just this squared, okay? It's not. And the reason why is because think about what this is. This is 1 plus x squared plus x cubed plus forever, right? And we're multiplying that times itself. 1 plus x squared plus x cubed plus forever. So how do you multiply this out? Well, you have to like FOIL it or expand it, right?
And we don't know even the endpoints of it.
Yeah, 1 times that, 1 times that. Then you have to do that infinitely many times. And then you do x times that, x times. But there's an infinite number to do here. It's hard to do this. Now there is a way, but we're not going to. That's actually later. That's in 8.7. 8.7 at the end of 8.7, which I doubt we'll even get to. Okay, so no go here. So this example is just to show you just how crazy things can get with this. All right.
One last thing, Professor, before we continue on this. So the radius of convergence, that's just a number, and we always get it basically by knowing the range or the limit on x on each problem.
Yes.
Is that what it is?
Mm-hmm.
Okay.
Yep. So like in the previous one, we had this piece right here, which was very important. And then what we did is we got the x by itself, and that number became our r. And if you go back and look at the graph, notice that when we talk about radius of convergence, the radius, think of like a center of a circle, right?
Mm-hmm.
So it's like here was the center at 0, because remember, this was a power series centered at 0. If we were to think of a circle with a radius of 2, you can see these edges are 2 units apart. Does that make sense? It's 2 in each direction. That's where the terminology comes from, radius of convergence. It's a weird it's a weird name, but
Is there cases when the radius of convergence is infinite?
yes.
There is.
Yeah, we already did one of those.
Yeah, so that only happens whenever the range or the domain, it's from infinity to infinity? Is
Yes.
that the case?
Yes, that's exactly the case.
Okay.
And does that make sense? Because if your interval goes in both directions forever, then your radius is infinite.
Mm-hmm.
Yeah.
Got it.
Okay. Okay, so for this one, we actually, there's not an easy way to do it. I have to show you something first. Okay. So this, I'm going to go to a new page, and I'm going to talk about very important topic, term by term, not trims, term by term differentiation.
Like
And
differentiation by
integration.
parts.
Oh. Differentiation and integration. All right. Here we go. Given any power series, which looks like this. So I'm writing out what you already know. This is what would happen if you start plugging numbers in for n. All power series look like this, right? Every single power series looks like this. And I can't stress this enough. The only thing that makes functions different, all right, is these numbers. Every function that has a power series is going to look like this. So the only thing that really distinguishes them from one another is the numbers that are sitting in front of the powers of x. Do you remember me showing you the sine and the cosine and showing you that sine had a bunch of odd powers of x? And
Yes.
that cosine had a bunch of even powers of x? That's because, well, you'll see, but they both have powers of x. It's just all that's different is the numbers in front. So we'll see. All right, so here's a general power series. If we define this to be a function, I forgot to put in here, given a function equal to this, let's say that that's given to us, then let me ask you this. What would the derivative of that function be? Okay, well, let's just go through it. Let's just go through this. Because it's addition, I can do derivatives one at a time, right? That's a rule that we have with differentiation. So what's the derivative of this? C sub 0 is just a number, isn't it? So derivative of that would be? Zero. Okay. Plus, okay, C sub 1 is a constant, isn't it? It's a constant. And so I'll just bring it for the ride. Times, now what's the derivative of x minus a? Well, derivative of x is 1. Derivative of a is 0. So this is just 1, right? When we take derivative, so it's just c, it's just 1. Plus, okay, c sub 2 is a constant. So I'm going to leave it out front. And notice I left a gap here. I left a gap here for a reason. C sub 2 comes for the ride. When I take derivative of this, don't I have to do chain rule? Doesn't that 2 have to come out?
Yes.
Okay, so let's bring that 2 out. 2, and then I'll have x minus a, chain rule, to the first power, and then times the derivative of what's inside, which we already know is 1. Keep going. Plus, what number is going to come out on this one?
3.
3 is going to come out. 3, c sub 3, x minus a squared. Any guess as to what the next one would be? We didn't write it down, but can you like kind of see a pattern here?
Yeah,
Well,
4c4,
4 c sub 4
x minus a to the cube.
plus dot dot dot. Yeah. Okay, now I know that this this looks weird, but check this out. I'm going to help you out here. I'm going to get rid of the 0. Do you all agree that this is the same as, watch, this is the part that's tricky. That first term, you don't need to rewrite all this. This 1 right here, I'm realizing that that 1 is really x minus a to the first power. I mean, to the 0 power. Okay, I'm just realizing that I could write it that way. And the reason I did that is because if we now rewrite this in sigma notation, then do y'all see that there's a lot of things that we have in common here? Like, look, there's a 1 in front of this. There's a 1 there and a 1 there. And then here it's 2 and 2, and here it's 3 and then 3, and then this is 4 and then 4. So if I start my sum at 1 to infinity, won't that coefficient out in front always just be n times and then c sub n? Y'all agree with that? That takes care of all of the stuff in yellow, right?
Correct.
And then x minus a to what power?
N.
So what are our powers?
N
0,
n minus 1.
n minus 1, right? It's always 1 less. So n minus 1 here. That would be the formula, wouldn't it? So here's what we're saying. If we start with an original power series, we take its derivative with respect to x. So the derivative with respect to x of this is equal to sum n equals 1 to infinity of n times c sub n x minus a to the n minus 1. Can somebody tell me what this looks like?
Geometric.
No. No, this we're taking the derivative of all this, and what wound up happening? Like, what did we do?
Right. Oh my
Power
God.
rule.
So
Chain rule.
chain rule.
Yes, I think you're right. If I took back in Cal 1, if I said take the derivative of x to the n, you would say what?
N times x, n minus 1.
To the n minus 1. You learned that rule very early in Cal 1.
Power rule.
You'll see that that's basically what just happened here. We had all of this stuff to the n. And when we took the derivative, all that happened is that n came out front, right? There it is. And then we subtracted 1.
I mean, that's exactly what's supposed to happen.
That's right. That's what's supposed to happen. Exactly. Now, there is one big difference, though. Our index changed, right? It starts at 1 now instead of 0.
Because of the minus 1?
Because of the way I wrote it out, the way we set it up, the pattern that we established. Now, technically speaking, okay, technically speaking, if you started this at 0, you'd still be correct. If you started it at 0. And why would it still be correct? If I start at 0, what's the first term?
0.
0, so it's not even there. And then you go to 1 and then they start appearing. So it wouldn't be wrong to put n equals 0. But the standard protocol is that when you take the derivative of a power series, you do the power rule, bring the power out, subtract 1, but then you change the index to 1.
So what would happen if you took the second derivative?
Same thing.
So it'd just be n equals 1 again, or it would be like n equals 2?
It should go up again. It should go up again. Yeah. But what we would normally like to do is we'd like to make that n again. So we'd make this n, not n minus 1. So we'd have to do what I did earlier. I would replace all my n's with n plus 1s. Okay, that's what I would do. I'd replace all my n's with n plus 1s. That way this would become an n. And then I would take the derivative of that. But yes, you can keep going derivatives all day long. Now, how do you think integrals are going to work? Well, I'm not going to go through it because it's going to take me too much time.
So we just apply power rule on this?
Yeah, if you have a power series and you want to take the antiderivative of it. Okay, if you want to take the antiderivative of a power series with respect to x, the answer is exactly what you would think it is. It's the sum. This time the index doesn't change. It's still 0. And then it's going to be 1 over n plus 1 times c sub n x minus a to the n plus 1. Do y'all see that that's just the power rule that we have for integration? Right, same rule. You do 1 over n plus 1, the power to the n plus 1. Now we have to do plus c, because
So
if you do antiderivative, you'll have a constant.
basically all the steps you went forward with taking the derivative of 0, then 2c2 was to establish this concept.
Yeah, well, wait, say that again.
This f of x, the whole 0 plus c1 and all that stuff right here on the top was just to establish this concept of how we can get it. And
Yeah,
then how-
exactly. So I didn't show this, but if I integrated each one of these and came up with a formula, we would come up, we would realize that it just turns into this. I'm not showing it though, okay, because of time. All right, now how in the world is that going to help us figure this out, right? Somehow that's going to help us. So here's what has to happen. You have to have a voila, like eureka moment here. And that's why you have to see this, like someone has to show this to you for the first time. That way you know to pay attention for these things. What is the derivative with respect to x of this? Now, I realize that that's not this, right? They're not the same functions, but I do know, we know what the power series is for this in yellow, right? We know what the power series is for that, but just check this out. What's the derivative of it?
would
the
it be
derivative?
quotient rule?
Yeah, quotient rule. Okay, so the derivative of that would be derivative.
0.
You know what? I think I'd rather do it this way. 1 minus x to the negative 1. Isn't that what that really is? 1 minus x, just bring the whole thing to the top.
Mm-hmm.
Now take derivative. So negative 1 comes out. And then it's 1 minus x to the subtract 1 from the power, negative 2,
And
times the
negative
derivative of
1.
what's inside, which is
Negative 1.
negative 1. These negatives become positive, and then this whole thing drops back down. And look what you have. This
Wow.
is that, right? That is that. So here's what we have to kind of put together now. We have to say, wait a minute. This function is equal to the derivative with respect to x of this function, right? It is. That's what we just said. The derivative of this is this. So that is the derivative of that. However, if the absolute value of x is less than 1, then we can say that 1 over 1 minus x, that quantity squared, is equal to the derivative with respect to x of, what am I going to put here instead of that? What am I going to put here instead of this?
Sum is
Sum n equals 0 to infinity of
x to the n.
x to the n. See, the key here is that I'm restricting our domain now. So I'm allowed to convert that to this, because that's what this was all about. Remember, I said, don't forget this. This we're going to use for the rest of this section. I've made it look like shit now, but this was the idea, right? So anytime we see this, where'd it go? Here it is. Okay, so anytime I see this, so long as I make the absolute value of x less than 1, then this becomes this power series. And now, how do you take the derivative of this power series? How do we differentiate this? Well, power rule, right? This becomes sum n equals
1
1 to infinity of
n
mhm,
x to the n plus 1
and minus 1, because
minus
we're
1.
differentiating, right?
Yeah.
Which is just, let's just plug numbers in. What happens when you plug in 1?
Get 1.
1, what happens when you plug in 2? 2x, right? Plug in 3, 3x squared. Plug in 4, 4x cubed plus 5x to the 4th plus forever, right? We are saying that this function right here should be equal to that function right there, so long as the absolute value of x is less than 1. So if I go to Desmos right now and I graph this function and then graph this series, they should match up inside that little interval between -1 and 1. Are your brains hurting yet?
I
We're
mean,
about to get to good stuff. What's that? I didn't hear you.
so I'm not getting the point. Like, how is it possible?
Okay. So there's 1 over 1 minus x squared. There it is. Good old rational function from college algebra. If I focus all my attention right now between 1 and -1, right there, and start, there's that power series right there that we just came up with. It was sum n equals 1 to, it's going to be infinity, n times x to the n minus 1. If I start graphing that, there it is. That's the first one. That's 1. This is 1 plus 2x. This is 1 plus 2x plus 3x squared. This is 1 plus 2x plus 3x squared plus 4x cubed. And as I keep going and going, they start to become the same function. Only between -1 and 1. Weird stuff, huh? Weird stuff. All right, one more. Last one that we're going to do here is the function. I want find the power series for f of x equals natural log of 1 plus x. How in the world could that possibly be related to this?
Isn't that the no, not the integral.
Go
The
for it.
derivative?
It's close. Look, what would the integral of this be? Let's just ask. What is the integral of this? I mean, you're thinking that, Abe, because the antiderivative of a constant over a linear expression should involve a natural log. So I think it's a good thing to see, yeah, we should try and integrate this. Let's just do it. Maybe it'll help you if I pull a negative out of the bottom. If I pull a negative out of the bottom, it'll make it look like that, right? Changes that to plus and that to minus. And please, right, you're all Cal 2 about to be hopefully done with this class, passing it. I hope everyone knows the antiderivative of this is just negative natural log of x minus 1, right? So it's pretty close, right? It's pretty close, but not quite, right? Not quite. So, I mean, but we're on the right track. I mean, this somehow connects these two together. So why don't we do this instead? What is the derivative of this? What is the derivative of this function right here? That's just 1 over what? 1
U.
plus x, right? That's all it is, right? You all agree? Okay. But wait a minute, isn't that 1 over 1 minus negative x? See, I'm seeing that I have a plus here, but the formula has a minus in it, right? 1 over 1 minus minus. So this was just to help think. This is really where we need to go. We looked at that, we said, what's its derivative? Here's its derivative, but that's this. Now, can somebody tell me what that can be turned into? That can be turned into a power series, right? What power series?
Geometric.
Okay, what though? What is the actual
1 to the negative x to the n.
1, 2? I'm not sure if you said, I agree, negative x to the n, I agree with. That part I agree with.
Yeah, I just added 1 in front of it.
Yeah, okay, yeah, so you put a 1, that's okay. So again, this goes back to the same thing, and maybe if it didn't burn in your brain enough, here it is. If you have 1 over 1 minus u, that is equal to 1 plus u squared plus u cubed plus dot, 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 which equals sum n equals 0 to infinity of u to the n, so long as the absolute value of u is less than 1. So it doesn't matter what's here, that's what goes right there in the formula. Whatever's here goes here. And the absolute value of that has to stay less than 1. So here we had negative x, so that's what goes here. Now, there's one more thing I need to do here. I'm going to write this as negative 1 to the n, x to the n. The reason I did that is because, remember, all power series, you have to have a c sub n, and then you have to have the x minus a to the n. So I needed to peel that negative away from the x, and that's why I split this up. Are you all okay with that? Okay, so look, is this the answer? This power series is not that function, right? This power series is not that function. What function is it? This power series is the
derivative.
It's the derivative of that function. So how do we get that function?
You have to integrate the series.
We have to integrate it, right? We have to integrate it. So what we can say is this: the integral of 1 over 1 plus x, right? Or we'll say the original function, natural log of 1 plus x, okay, that's the original function right here, is equal to the antiderivative of this, because this is the derivative of that. But that's just equal to the antiderivative of that written as a power series, which we just said was sum n equals 0 to infinity, negative 1 to the n, x to the n. I need to take the antiderivative of that. And that should be, okay, so when we do the antiderivatives, all we're going to do is power rule. I leave the negative 1 to the n alone. I put 1 over n plus 1, negative 1 to the n, x to the n plus 1, and then plus some constant. So please pay attention to the fact that when you're doing antiderivatives, this c sub n, you don't touch it. Okay, you don't do n plus 1 on that. You only do n plus 1 on the x. This part stays the same. Now, I'm actually going to write out the first few of these just so we can see them. If n is 0, I'm going to get x. If n is 1, I'm going to get minus, and I'm going to get 1/2 and x squared. And if n is 2, I'm going to get a plus, I'm going to get a 1/3, and I'm going to get x to the 3rd. And if I do 3, I'm going to get 1/4, minus 1/4, x to the 4th. Okay, I see the pattern. Plus dot, dot, dot. There's the power series for that function. There it is. Now, let's go look at it. Here's natural log of x, or natural log of 1 plus x. There it is. If I just look between negative 1 and 1, here comes the power series, and there it is. All right. So I still think that I have not sold you on any of this yet, that y'all are kind of looking at me like, what's the freaking point of all of this? It's okay. I want to look at, where's the one that we have? No. Okay, I want us to look at this one right here that we did earlier, right there. Want its power series. Where did we put its power series? This one right here. There, right there. Copy. Okay, the function was x cubed over x plus 2. And what we determined was that the power series for this was this. Now, we didn't write out the first few terms, but I'm going to do that right now. If I plug in 0, I'm going to get 1/2 x cubed. If I plug in 1, I'm going to get negative, help me out.
Uh,
1/8, I think.
You're plugging in 1 now.
Oh, 1. Oh, it's going to be
Okay.
negative 1/4.
Negative 1/4 x to the
4th.
4th. Okay, next one will be a plus. So now we're plugging in 2.
1/8.
1/8 x to the 5th
5th.
minus 1/16 x to the 6th plus 1/32 x to the 7th minus ... There's a pattern here. Do y'all see it? The bottom is growing by factors of 2, right? Doubling each time, alternating. Yes? So check this out. What's the integral from 0 to 1 of x cubed over x plus 2 dx? All right, so you go try and integrate that. Go break out your integration by parts, or do whatever the hell you want to do, okay? Go do it. And good luck with that. It's going to take you probably a very, very, very long time. But this should be equal to the integral from 0 to 1. Remember, this and this are the same so long as you're within the interval of convergence, which was, I believe, you had to be between, I think we said x had to be between -2 and 2. So as long as this integral is between -2 and 2, which it is, then I can use this power series instead. Dx, and now take the antiderivative of each of these. Okay, that'll be 1/8 x to the 4th. So I'm just using power rule on each of these. Minus 1/24 x to the 6th plus 1/48 x to the 6th. Oh wait, I messed that up. That should be, I messed this one up. That should have been a 4. I apologize. I know I'm moving fast, okay? Plus ... and I evaluate that 0 and 1. So all I have to do now is plug 1 in here, plug 0 in here, and I've got an approximate answer to the area underneath that curve, right? That's what I would get. So you may not think that that's very valuable, but this is the way a computer works, okay? In fact, when you go to Wolfram Alpha and you type in integrate x cubed over x plus 2 on the interval 0, 1, you got this answer, 0.0896, right? How to get that answer? It used the power series and just plugged in. That's why it says approximately. Also, if you just type in, like forget the integrate, just take out integrate completely and just type in that function. Just type it in right there. If you hit enter, this is mind-blowing about Wolfram Alpha. This technology was not here when I was in Cal 2. So here's the function, right? If you just scroll down a little bit, look at that. It gives you the power series. There's the power series, x cubed over 2. Is that what we had? It doesn't look familiar. Oh, yeah, that is what we had. X cubed over 2 minus x to the 4th over 4, right? Minus x to the 4th over 4. And then we had what? x to the 5th over 8, right? It's, I mean, you can just go get the power series. It's crazy. All right, what time is it? 20, we have 15 minutes. .6, I'm keeping it very simple in this section. All right, we are not getting to the harder problems. Problems 3
So
through
these
9.
are the easiest problems
Well,
on the section.
yeah. Yeah. Yeah, but I mean, all of these, yeah, just work through 3 through 9. Okay, if you want to do 10, you can, but 3 through 9. Those, all we're doing in 3 through 9, all you're going to be doing is you're not going to be messing with this derivative stuff. You're just going to be doing like what we did on this one. Pull out the x cubed, rewrite this, make it a minus, things like that. You're not going to have to recognize, like I did on this one, like you're not going to need to recognize that that's the derivative of something. Or like on this one where you're going to have to recognize that that's the antiderivative of something. Those I'm not going to give you. Those are harder, all right? The basic idea is here. This is the basic idea right here. So the thing is, like, you'll be in an engineering class, okay? You'll be in some engineering class down the road, and you're going to see them do this. Approximately. Okay, they're going to write 1 over 1 minus x is equal to approximately equal to this. Do not be that student going, what the fuck? You know, like, what is that? No, that's just converting it over to a power series and approximating it with the first few terms. Okay, if you don't know that, it's going to look like magic. It's going to look like, how could this algebraically be the same thing? Right? Like, how in the world can that be the same thing? Do you agree? That would look really strange, very alien to you. You don't want to run into that later. You need to understand that this, now, of course, there is a condition here that only works when that's less than 1, but it is valid, okay? All right. So we are now in 8-7. Looking at the clock.
Are you gonna have office hours next week for questions?
When's our
Or-
final?
Or when? Yeah, I don't even know.
Let me talk
Next
about it
Thursday.
because finals week is never normal. Because like I'm giving a final that goes from 9:30 to 12:15. Normally I'm done with that class at 10:45 and I'm in my office hours at 11. That won't happen. So I'm not going to have normal office hours. I'll have some office hours, but it won't be normal office hours. I'll let y'all know.
Yeah, I
Okay.
think we have the final on the 10th.
Okay. So yeah. All right. So look, 8.7 is something called Taylor and Maclaurin series, but we don't have a lot of time, so I'm just going to kind of get to this. If we're given a function in its power series, we know that all power series have to look like that, right? That's the general form of a power series. In the previous section, I gave you an example of a specific function, and we came up with its power series, right? Because it happened to look like a geometric series. But the idea is, in general, if somebody hands me a function, can I generate its power series, right? That's the question. And I told you, it all comes down to this C sub n. Is there a way to figure out what that C sub n, what the formula would be for a particular function? So like, for example, if somebody gave me the function f of x equals sine of x, well, that should be equal to some power series, all right? But I don't know what this is, okay? If I knew what that was, then I would have its power series, but I don't know what that is, okay? So this was a huge problem, and people toiled with it for a long time, trying to figure out a way to figure out what those constants are. Well, I don't have time to show you, okay? If you want to see it, go to my YouTube channel and click on my Monday, Wednesday Cal 2 class from yesterday. I did show it, okay? But it takes about 15 minutes to show it, all right? I'm just going to give you the formula. So I'm selling you short in the effort to show you more, okay? So here's the formula. It's called Taylor's formula. I've never done this before. I've never skipped showing it, all right? So I want to see how this goes. Taylor's formula. Taylor figured out that C sub n will always be equal to the nth derivative of the function at a over n factorial. It's not that hard to show this. It just takes a little time. So keep in mind here that this little parenthesis with the n in it, that stands for the nth derivative of the function. The nth derivative of the function. Now, I'm just going to jump right into this. There's the formula. I'm going to just give you an example and see how you do with this. And I can't begin to tell you how absolutely monumental that is right there. It's absolutely incredibly powerful. So let's take the function f of x equals sine x. And let's find the power series about x equals 0. Now, remember, when I say about x equals 0, this really represents what number? The 0 is the what in the formula?
A.
It's the a, okay? Keep that in mind when we're trying to find this power series about a certain point. Okay, so according to Taylor's formula, the number that goes out here is just the nth derivative of the function at a. Okay, well, let's start looking at derivatives of this function. So what we're going to do is we're going to make a list, a table. So the first thing on my list is I'm going to take the 0th derivative of the function. What is the 0th derivative of sine? Well, that just means don't take the derivative, right? You may not have known that, but that's what it means. Now let's take the first derivative of sine. What's the first derivative of sine?
Negative cosine.
Cosine, right? What's the second derivative of the function? Now just take derivative again, right? Negative sine x. And now we take the third derivative. That's negative cosine x. Now we take the fourth derivative. And we get what?
Sine x.
Sine x. And now things are going to repeat, aren't they? Everything's going to repeat. The next one will be cosine, then negative sine, then negative cosine, then sine, then cosine. It's just going to keep doing the same thing over and over, right? Okay, so those are what the derivatives look like. Now what I'd like to do is figure out what these derivatives are at a. So what is the derivative? What is the 0th derivative of the function at a? A is 0 here. So what happens if I plug 0 into this? What's sine of 0? 0.
0.
Okay, what's the first derivative at 0? So what is cosine of 0? 1. Okay, what is the second derivative at 0? Plug 0 in here. We get 0. Okay, now what is the third derivative at 0?
Negative 1.
Negative 1. What is the fourth derivative at 0?
0.
0. And now it's going to keep repeating, right? We're going to have what? Next one will be 1, then 0, then negative 1, then 0, then 1. Got it? It's just going to keep repeating. All right, so according to Taylor's formula, sine of x should be equal to the sum n equals 0 to infinity of c sub n, right? That's this yellow part, and that c sub n is this formula, which is the nth derivative at 0 over n factorial x to the, or x minus a, which is x minus 0 for us here, to the n. All I've done here, is replaced the c sub n with that formula right there, and I replaced the a with 0. Is that all right? Okay, let's start cranking this out, everyone. Let's start cranking this out. This should be equal to, let's start at n equals 0. What happens if we plug 0 into this? For n, we get the 0th derivative, right, at 0. What was the 0th derivative at 0?
0.
It was 0, so I get 0 over what?
0.
0 factorial, right?
Which is 1.
Which is 1. And then x to the 0. Yes? That's what we get. Now we let n be 1. So when I plug in 1, let's see what I get. Okay, what is the, what, if I plug in 1 here, that's the first derivative at 0. What's the first derivative at 0?
1.
1 over
1
1 factorial x to the
1.
1.
1. Okay, keep going. Plus, okay, now we plug in, where are we? That was n was 1. This was n is 0. This was n is 1. What about n is 2?
2 over 2 factorial x to the 2.
Not 2 over 2
over 2.
factorial. Yeah, the second derivative at 0 is 0, isn't it?
Oh, okay.
Right, so we get 0 over 2 factorial x to the second plus, okay, now we go to 3, the third derivative at 0, which would be
-1 over
-1 over
third factor, 3
3
factorial.
factorial x cubed. And now it's going to keep repeating, right? Now we're at the fourth, so we have 0 over 4 factorial x to the fourth. What would the next one be?
First term.
1 over 5
1 over
factorial.
5 factorial x to the fifth. I'm running out of room, plus dot, 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 right? Now I'm going to get rid of a bunch of stuff because we have a bunch of zeros here. Sound effects are optional. Okay, now that's everything that has zeros. So I'm left with this one right here, which was just x. This one right here is -1 over, I'm going to leave it as, you know what? I'm going to leave the factorials here. Let me leave the factorials here. You'll see why. 1 over 1 factorial x to the first power. And then this next one becomes -1 over 3 factorial x to the third. Then plus 1 over 5 factorial x to the fifth. Can you all see the pattern? What would my next one be?
7.
-1 over 7 factorial x to the seventh plus dot, 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 right? Which, if I wanted to write this as a sum, I know you were all very capable of doing this. Let's see if you can. You have, all of the numerators have 1s, so 1 over. Now tell me about these factorials. 1 factorial, 3 factorial, 5 factorial, 7 factorial.
2n
plus
minus
1?
1 factorial.
2n,
Minus 1.
remember where we're
Minus
starting. Remember where we're starting.
Oh,
We're starting
2n
at
plus
0.
1
2n plus 1
factorial.
factorial x to what power?
And
1,
2n plus 1.
2n plus 1 again.
Okay, Jesus.
Good. There it is. That's the power series for sine. There it is. Now, I'll put this screen back up so you can, and I'll send you all these notes. On your formula sheets, Maclaurin series. Wait a minute, hold on. We forgot something. We forgot to take care of the alternating part. Hold on. It alternates. I missed that. My apologies. It was plus, then minus, then plus, then minus. We need to account for that. So we need a -1 to what power? Because we need it to go positive, then negative, positive, then negative.
n+1.
N+1.
N+1 will work. Okay. My fault. Sorry. I'm looking at the clock. I'm out of time. So if you go back to your formulas now and you look at sine x, check this out. There it is. That's what we just got. -1 to the n. Oh, wait, hold on. Oh, we're starting at 0. My fault. I'm too crushed for time right now. That's what happens when I'm crushed for time. Why do I have to change it to n? Not n+1.
Because we start at 0.
Because we start at 0. Yeah, if we were starting at n+1, then of course we would start. If we were starting at n = 1, then we would start at n+1. But because we're starting at 0, we want it to stay at n. Okay, I'm out of time, but I know all of you are enjoying this so much that you want to see it. So here's sine x, the graph. And now we're going to do the series that we just came up with. It was -1 to the n, and then it was x raised to the 2n plus 1. And then it was all of that divided by 2n plus 1 factorial. And we need to add a slider here. We need to make this go from 1 to, let's say, 30. We don't even need that much, probably just 20 by 1. There we go. Okay, you see the blue? Here it comes. Here's our power series. That's it. Now, you know what's cool about this? There's no interval. The radius of convergence is infinity for this power series, which means this power series is valid always. You don't have to like move it around. And if you look at your formula sheets, maybe this makes a little more sense now. All of these power series that you're looking at for E, for sine x, cosine x, all these, most of them have radius of convergence. Well, not most. The ones that matter, E, sine, cosine, those are the ones that matter. They have, yeah, okay. I'm wiped out, man. I'm wiped out. You're wiped out too. So homework, you know what it is. Get caught up through 8.6. Do the first couple of problems through 8.6. Thursday, we'll hit it again and try and get through a little bit more here in 8.7. And we'll talk. My plan is to give you a review, like an actual review. All right.
When do you think that you will like finish the review and be able to publish it?
I don't know. I'm going to try for it in the next day or two.
Okay.
Yeah. I mean, your test is on the 10th. Is that
Yes.
what you said? Okay. Well, at least it's not on Tuesday.
Fortunately.
Yeah.
Yes.
Yeah. All right. Well, you know, it is what it is. Let's call it a day. Any other questions? I'll hang out here for a minute if you need to talk.
Thank you very much.
All
I'll see
right.
you on Thursday.
Yep. See you. Thank you.
Thank you.
Thank you. Have a nice day.